Have you ever heard an ambulance passing by or a jet flying overhead and noticed the pitch of the sound that it emits changes as it approaches and subsequently leaves? Perhaps you chalked it up to a trick of the mind, or didn't put much thought into what may have caused this strange phenomenon. What you experienced was not an illusion, but a real-life example of something called the Doppler effect. The Doppler effect is a change in the observed frequency of some kind of wave, whether it be light, sound, or other, because the source of that wave is moving relative to the observer. The points S0, S1, and S2 represent the source of a wave at different points in time, and are color-coded to match the waves given off when the source was at that position. The point O represents the observer, who does not move. As you can see, although the frequency at which new waves appear is constant, depending on the position of the observer, the measured frequency is different because the distance between waves can either be stretched out or compressed by the movement of the source, either catching up to or receding from the waves. In this case, the source is approaching the observer, so the wavelength appears compressed, and therefore the frequency is Doppler shifted up. It's possible to figure out the degree to which this happens by deriving an equation that describes the Doppler effect, shown here. Assuming a one-dimensional environment and a source that moves at a constant speed towards the observer, we set up the equation by putting the observed wavelength on one side and the wavelength of the source on the other. We also add the negative change in the source's position during one cycle to the right side of the equation because it factors into the perceived wavelength on the observer's side. From here, you can decompose the wavelengths into velocity of the wave, which will always stay the same, times its period, which varies depending on whether or not you're the observer. You can decompose the position delta into the velocity of the source times the period of the source. Now the bulk of the work is done, and the rest is just moving some variables around and converting the periods into frequencies. Now we have a way to calculate the frequency of a Doppler-shifted wave coming from a source that is moving towards our observer. We can apply this to a sound wave coming from a moving vehicle, which is what Tony will do in the next section.
In this scenario for the Doppler effect, we have our observer, which is Luis, and our source, which is the truck. The source is approaching a standstill observer. The truck is moving at 5 miles per hour or 2.235 meters per second. Using the application Firefox, we were able to calculate the peak of the siren's frequency at 1007.8 hertz. Since the speed of sound is 343 meters per second, and by using the Floridian method, we are able to calculate the frequency of the observer using this Doppler equation. The experimental frequency at the observer was 1013.6 hertz. Again, using the Firefox application, we were able to calculate the actual frequency being 1031.25 hertz. Using the percent error formula, we calculated our experiment had a 1.7% error.
So in the same way that we were able to quantify a change in frequency using the Doppler effect formula, the same principle can be used in devices like police scanners and weather radars. In the same way that we were able to measure the frequencies of the sound waves coming from the car, we can also measure the sound waves that the car hears coming back. And these radars measure the time it takes for waves to bounce off objects and return back to them. With this time, you can determine both the new wavelength and frequency. And using the initial and the final wavelengths, the radars determine the speed of the objects using the Doppler shift phenomenon with the given wavelength shift. Weather radars use this to detect the speed of wind or rain, allowing an accurate report of severe weather.
This was the Doppler effect by Tony, Tim, and Luis, and all sources are linked below in the description.